Homotopy invariance in string topology.
Okay, thank you. So I have a whole two sets of organizers to thank. The workshop organizers, yes, but really the program organizers have been harnessing higher structures for 6 months and enjoying it a lot. And as you can see, this one of the things we learned. I'm not sure what harnessing higher structures mean, but what I've learned is to write my title and my co-authors before we start the talk, because this has been a hard training. We had gong shows every Thursday and with strict rules, and anyway, thanks a lot. Good. Homotopy invariance, yeah. Where was I? So I'll do manifolds, right? It's a conference about manifolds, and I don't have anything against topology. So no worries here. So M is a manifold, closed, oriented. And I want to talk about string topology. That's about the loop space. So M is the maps from S1 to N, the loop space, free loop space. And string topology is something about writing down operations on the homology of this space. So the two main operations, or big main operations in string topology. The original one of Chas-Sullivan is a product on the homology. So if I put HP LM tensor HQ LM, it goes to HP plus Q minus N of LM, where N is the dimension of the manifold. And then there is a homology coproduct or cohomology product. It's a little bit nicer to state as a cohomology product. Goresky-Hingston, write a product, so cohomology HP upper P LM tensor HQ LM to HP plus Q plus N minus 1 of LM. And maybe you have seen this slide variant with relative groups. Really, they write this as a homology relative to the manifold seen as the constant loops, like this. And really, this is the main part, P plus Q plus N minus 1 LM relative to M, so it will become relative later. You can always just extend this to be zero on the constant loops, and so this is sort of having the one or the other is essentially equivalent. Okay, so before I start talking about homotopy invariance of these structures, let's talk a little bit about what sort of things we do with them these days. So a main one of the motivations for studying loop spaces is geodesics. So geodesics, they're all closed. Closed geodesics correspond to critical points of the energy functional on the loop space. I choose the right model for my loop space. And well, yeah, so one may try to critical points, and this is what Morse was inventing Morse theory for, is to study to get information about the critical points by looking at the homology of the space, hence about the geodesics. And one needs to know fine information about these things to really, to get a lot of information out. One has to know finer information than just the homology. So this has been a sort of a theme in some of the work in this area. And so, for example, Goresky, let me just write GH for Goresky-Hingston. I wanted to give them names. This product and this one. These two operations, they know about index growth, index growth of critical points of critical points geodesics. So if you have a closed geodesic, then you can iterate it and run it many times, and it will create many. It's still a geodesic when you iterate it, and so one critical point will create infinitely many critical points, and you may wonder, how does the index vary? And so Bott did some work very long ago on this with some sort of range of indices, and you can use the product vanishing or non-vanishing of these products to know whether your index growth is minimal or maximal. So which is the sort of finer information I wanted to mention. I also have work with Nancy Hingston, where we show that this coproduct, homology coproduct or cohomology product, knows about, well, what we call intersection multiplicity of chain representatives of, let me not try to write something about when you have a homology class in the loop space, you may ask what sort of loops you find in chain representatives, and how much how much iterated multiplicities they have, and again the vanishing or non-vanishing of this tells you about that sort of information. Yes?
So what are the possible index growths of these iterated geodesics? I mean,
there is a range.
Yeah, but is it linear? Is it quadratic?
There's a linear range. There's a linear range. I don't know it like that, but this is like there's a range that goes back to Bott. Okay, so these are sort of one type of information, and also just to, it's good to know these things are non-trivial. And so, as an example, if you take the homology, so this is Cohen, Jones, Yan. If you take the homology of the free loop space on a sphere where n is odd, as an algebra over the Chas-Sullivan product, this is generated by just two elements. It's an exterior algebra on one generator, tensor polynomial algebra on another generator. So it's a very simple presentation, and Goresky-Hingston show that actually in cohomology you have a very similar formula. So cohomology of loop space of Sn relative to the constant loop as an algebra over this product, cohomology product, it also looks like this. So I don't know, they call this little u tensor z t, but now you have to truncate, get rid of the bottom part of this thing. But anyway, it looks very much the same. And in particular, it's a very non-trivial structure. And maybe, so one last thing I wanted to say, and this is like not, this is not an actual statement, and I don't know what the correct statement is, but roughly, to be made precise, so this is not the sort of, I want to say something like string topology operations, whatever this is, so there I know what I mean, but I won't make it precise, are generated by, well, this product, and this other product, maybe the dual. So let's say in homology, so I take the linear dual of the Goresky-Hingston product. Then you have an operation coming from the S1 action on the loop, right? If I have a loop, I can recompose by a rotation. This gives you a degree 1 operator in homology. And then you have power operations, which is this repeating a loop. And this is probably not quite true as such. I mean, I probably have to write a little bit more here, and we don't know exactly. I don't, you know. But morally speaking, anyway, that's what it feels like. Good. So, yeah. Now the original hope of at least Dennis Sullivan was that this product, this Chas-Sullivan product, would know about the differential, would know something about the differential structure, the smooth structure of the manifolds. And so, but this is, so this is not the case. This is a theorem that was, I mean, there are several proofs, Cohen, Klein, Sullivan, Brewer, Salvatore, and also Crab. And I guess if you go rational, you can also get Felix Thomas, the Chas-Sullivan product is homotopy invariant. So we are, of course, homotopy invariant. So we have also had another sort of recurring discussion in this harnessing higher structure program was, you know, there's in the seminar room there's this thing that the light goes on and off depending on where the board is. We haven't completely worked out how, but Jesper keeps saying it's not a bug, it's a feature, right? And he claims this is Stefan's, right, one of the organizers. And you know, I'm not sure what I think of it, but I want to say this is not a bug, it's a feature, right? This is, it's like, well, is it a sad thing that it's homotopy invariant? I don't know. I mean, maybe it's not a sad thing, because whenever you then find out something that these products or coproducts detect, then it just means these things are homotopy invariant, which is a feature, right? Okay, so we won't be too sad, but you know, there was still some people were sad, and so there was a sort of there was a next hope after the first hope, which was maybe so-called compactified string topology can do better. Okay, and as an explanation of maybe compactified string topology can do better. Example, e.g. this Goresky-Hingston product, coproduct, whatever. Coproduct, co-it. So this would be an example of such a compactified operation, and so, well, theorem. So this is what Nancy and I prove. No, so the Goresky-Hingston product, coproduct, I don't know what to call it. Yeah, okay, it's a product in cohomology, it's a coproduct in homology, right? Everybody happy? Right, that's what I mean. Product. It's also homotopy invariant. Yeah. Okay, so that's what I want to talk about. To explain a little bit the sort of things that come in proving such a theorem, and I will also talk a little bit about the difference. What gets more. Why should this compactified thing be more hopeful or maybe more difficult? Then it's best to do a warm-up, which is these products are based on the intersection product. I mean, this is a main ingredient, so let's think a little bit about the intersection product. I still have one more board. So the first thing I want to do is to pick a Riemannian metric on M. I can always do this, and as we're anyway going to show homotopy invariance, I'm allowed to pick any structure I like. They won't matter, okay? And once you have one of these, this is useful to have. For example, so when you look at M sitting inside M cross M as a diagonal, so this has a so-called tubular neighborhood. So here's the diagonal copy of M, tubular neighborhood. You should have this sort of picture in mind. What does this mean in practice? It means there's a bundle over M, which is all these lines. The bundle is, this case, the so-called normal bundle. In this case, it's just it's isomorphic to the tangent bundle of M, and there is an embedding of this bundle, which extends, the embedding of M as by a neighborhood. Okay, so there is such a thing. Let's call this nu. And just to make clear that this is very, very explicit, so you can define nu of, I have a point in M and a tangent vector, and I'm gonna take my tangent to be tangent vectors to be at most of length epsilon, and epsilon is smaller than the injectivity radius of the manifold. I can just define this to be the points M. I just keep one the point I used to have, and then I exponentiate at M the vector, which means I have my point and my vector, and I just push. I create a new point by pushing along the vector, writing the geodesic. Okay, so that gives you a neighborhood, and the image, the so-called tubular neighborhood, which is like, by which I just want to mean the image tubular neighborhood. Nu of the image of this tangent bundle is just is the set of M1, M2, such that the distance between N1 and M2 is at most epsilon, and I'll just call this U epsilon. Okay, so this is a very explicit, simple construction that we can make. So one can use this to define the intersection product by doing a Tom collapse map. The idea is you want to invert in homology the diagonal. So we have this diagonal map, and we want to have our diagonal here, and we want to turn it around in homology to have a product. And this is so when you have such a bundle has a Tom class Tm, which is in, well, if you think in terms of the bundle, it's in Hn of if this is your tangent bundle of vectors at most length smaller or equal to epsilon relative to those of length equal to epsilon, so this bundle modular relative to the sphere bundle, but this is isomorphic to Hn of m cross m relative to the complement of this epsilon neighborhood. This is my u epsilon here, and I may as well look at it over here. Okay, so then the intersection product well, I'll write this, I'm doing this in part because there are things I don't have to do again. So, you first need your Kunis map, and I'm working with integral homology. If I want to do a coproduct, I'll be in trouble writing such a map. Okay, they are the issues of the Kunis whatever. But from now on, my products, they will start here, and then you can worry about whether you have a map or whether you have to invert something. But this is what you would do. Here there is always such a map, also integrally, and then you go relative to this u epsilon complement, and then because your class is relative to this thing, when you cap, you could just do one. Really, then we have done everything. This is like closure of epsilon, boundary, whatever. You can, by excision, you can get rid of whatever is far away from u epsilon, and then the cap product, you can just cap, and then you land in h star minus n of u epsilon. But this is, because this was like a bundle over n, this is isomorphic to h star minus n of n. Okay, so that's your intersection product. Okay?
One question, one could think that you only need the spherical vibration underlying this tangential bundle to write this down. Maybe it's not true, and then you would see why it's homotopy invariant. Of course, something is wrong, I understand, but...
So this is very easy to show is homotopy invariant?
Yeah. Yeah, I thought...
But you're saying...
I was saying, I think about Poincare complexes P-Barker bundle as homotopy invariant.
Yes.
The normal bundle isn't. That you can do something where you replace...
I mean, my wish is that at the end of the talk you tell me, but right, because my first...
more complicated, but I just want to see what's going wrong.
My first guess was like, this is easy, right? And then I got into trouble. So I'll explain the trouble, and then you tell me if you can get rid of this. Yeah, okay. So, fact, the intersection product is homotopy invariant, and so Wolfgang wanted a proof.
Yeah.
I was going to write the whole proof in full details, but no, sorry. But what is the proof, right? Well, actually, it's you can define it equivalently. So there's something to show here as the Poincare dual. But it's not a difficult computation. Poincare dual of the cup product. So there's a sign issue, but a controllable sign issue. But anyway, we're just talking about homotopy invariance. It is you can just use Poincare duality in the cup product. The cup product is happily a homotopy invariant. Poincare duality is going to be compatible. Everything is totally happily compatible because the homotopy equivalence takes the fundamental class to the fundamental class. So this is easy. Good. So now we are happy with the intersection product, and so we are ready to move up to the loop space and do some. So everybody is trying to find the easy proof, right? So not just Wolfgang. Okay, so Cohen-Jones wrote this definition of the Chas-Sullivan product, which is just a lift of this intersection product. They say, well, you know, you have Lm cross Lm living over m cross m if you evaluate your loops at the base points. Inside, so here you have the diagonal, and what is the pullback over this is the space Lm cross over m Lm, which is the pairs of loops which agree at the base point. Okay, and what they say is, well, there is also, this is a codimension n condition where the 2 points do agree. It's just 2 single points in the manifold. So this is a happy codimension n condition, and there is a tubular neighborhood of Lm cross m over m over L, whatever, of this thing inside Lm cross Lm, and so you can define the Chas-Sullivan product in the same way as we did the intersection product. You start with the homology of Lm cross Lm, and then you go to, you know, relative homology, if you like, Lm cross Lm relative to, well, some complement of some epsilon neighborhood, which is this tubular neighborhood, and then you cap with the Tom class of this bundle, and you get into this neighborhood, which is minus n, which is isomorphic to the homology of Lm cross Lm over m. And now you have loops that agree at a point, and if you have 2 loops that agree at a point, then you can run the one and then the other. You can take the concatenation and you get into the homology of Lm, single copy. Okay, so that's one. So then we have this coproduct in homology of Goresky-Hingston. It is a little more tricky because it's not exactly so nicely codimension n. The idea is sort of the same. You have a, well, now we want to, instead of multiply loop, we have a loop and we want to cut it apart. And so we have, you know, here's some loop, I don't know nothing about it, and I would like to cut it apart. So I would like to look at, well, the subspace of loops where it self-agrees at some point. If you do this for just a self-agreeing at 1/2, you get a trivial product, coproduct, because self-agreeing at 1/2 you can shrink down to just self-agreeing at 0, and then it's almost 0 in homology. But if you let your point vary, so you look at inside Lm, you look at not inside Lm, but Lm cross I, you look at the loops and times such that gamma 0 equals gamma of S. So this is, you know, well, the picture looks the same as before, but now I'm looking at a self-intersecting loop. So this again maps to m cross m by evaluating at 0 and at my time S, and this maps to m because it's the same point. This is your diagonal. This is sort of a slightly more complicated situation because this is like, you know, so this is gamma, just fixed annotations, gamma 0, gamma S. This embedding is like codimension n when S is different from 0 and 1, but codimension 0 when S is equal to 0 and 1. Of course, you know, I shouldn't be doing this one S at a time anyway, right? So this is not really a meaningful statement, but still it says that, well, there's something a little funny. When my time here, S, my chosen time, goes to the 0, well, you know, every loop satisfies that gamma 0 is equal to gamma 0, right? So it's a slightly more complicated situation. So Goresky-Hingston go around this in two ways, actually. Yes?
Is it still the map from Lm cross I down to M cross M transversal to delta in some sense, or is that?
Well, not really, right? I mean, I don't know. What does that mean? Everything is infinite. Does that mean something?
My question, can you, I mean, there's...
I don't know.
Try to make it rigorous.
So I have three fixes for this. So two of them are in the paper. The third one is not written. You know, probably correct, probably doable. So one is you cap your loop space by the energy of the loops to sort of control, you know, it doesn't, loops that don't go crazy, and look at and don't work with the whole interval, but up to some, you know, epsilon distance from 0 and 1, and work with small loops, and you do a limit. So this is one of the constructions Goresky-Hingston do. A second construction which they also do is to replace, which is really cool. The more I think about it, the more I like it. It's you replace Lm cross I by Lm, and by just, if you have a map that takes gamma S to you take your loop from 0 up to S. Let me write this here. You take your loop as it is from 0 to S, and then you concatenate it with itself from S to 1, but you do this, you reparameterize so that this happens at time 1/2. And this means that, you know, if your time was 0, then you will have a loop that is constant for the first half of the time and then non-constant. If your time was 1, it's the other way around. You'll have a constant loop here. It's a totally fine map, and we have sort of replaced the boundary of the interval by these two subspaces of the loop space. Works. And here, once then our intersection is happening at 1/2, and there we can do a tubular neighborhood. Okay, so that's my fix number 2. There's a fix number 3, which is we probably can make, by modifying these spaces a little bit, we probably can make a tubular neighborhood, but this is really subtle, involve all sorts of subtle difficulties. So, what Nancy Hingston and I do is we show that you know, there's no need of tubular neighborhoods. So this is the sort of the easiest. The easiest fix is actually you never need these tubular neighborhoods. Why do you bother constructing them? It's fun, but except for that, you can define these. For example, maybe let me do the product. Let me do Chas-Sullivan product. How do you do this? Well, you have the homology of Lm cross Lm mapping over, well, I don't know, M cross M. What did we do? We went, when we did the intersection product, we went to M cross M relative to this U epsilon, but let me call this map E. Well, I can go to Lm cross Lm relative to E inverse, the inverse image of this U epsilon. Now, this map takes E inverse, complement, sorry, the complement of this neighborhood. This map takes well, this neighbor, the inverse image to this thing, and whatever. It's compatible with everything. So if I take my my Tom class, which lived in Hn of m cross m relative to u epsilon complement, well, E star will take it to Hn of Lm cross Lm E inverse of u epsilon complement. I can just pull back the Tom class, and if I cap with it properties of the cap product, I'm not using anything. I'm just pulling back the Tom class from here. We'll map this to E inverse of u epsilon complement. Then you have to ask what this is and how this relates to the loop space, and then we have to work a little bit, but not very much. So if we are in what is this? E inverse of u epsilon. Remember, these were the points here that were epsilon from each other, and most epsilon from each other. This is now inverse image under the evaluation map. This is the well, okay, let me just draw it, right? A loop and another loop, and somehow they are close by. The evaluation at the base point is close by, and in particular there's a unique geodesic here, okay, and so I have a happy retraction to Lm cross over m Lm, which I can then follow by concatenation, which, if you like, takes gamma 1, gamma 2, two loops to, well, I'm going to do gamma 1, and then I'm going to do the little geodesic here between the two loops, and then I'm going to go do gamma 2, and then the geodesic inverse. Okay, so I haven't had to do very much, just a little bit of something, but this gives me a map to. So here we went down in degree -72 Lm, and just to show you that this is just the same for the coproduct, so the Goresky-Hingston coproduct. Also, you see where the relative homology comes in. If I'm in homology of Lm cross Lm, Lm just 1 relative to the constant loops, I can cross with an interval, and here's your +1 in the degree of the coproduct Lm cross I, m cross I union boundary, well, Lm cross boundary I. So this is a happy map in homology as long as I quotient out by the boundaries, but this, yeah, the boundaries of the interval, and the boundaries of the interval will give me constant loops, and therefore we might as well map out by the constant loop from the beginning. Anyway, I'm in this space. This is now the space we had before here, and we were looking at this funny neighborhood, but instead of trying to do a tubular neighborhood here, we have the same map here to m cross m that evaluates the loop at 0 and at that time, and we can just as well look at the inverse image of this u epsilon complement and pull back the class and so on. So you'll get a, just as in the other case, we can cap with E0s with E0s pullback of the Tom class of m, and this will land us in H star plus 1 minus n of, well, the inverse image along this of u epsilon. Now I'm still relative to these things here, and what is this? It's very much like what we had before. It's what's in this space. It's a loop that at time s, it's a loop and a time, so that at time s, it's close to having a self-intersection. That's what it means to be in the inverse image of this neighborhood of the diagonal. And so just as before, I can recreate a new, now a pair of loops by taking one here and another one there by using the geodesic. So it gives you a map. Okay. Yeah, so we're not using very much to define these products and coproducts, and therefore they should be homotopy invariant. Okay. Right. So then you sit down and prove it. Right. Where were we? Yeah, that's the old one. But remember how we proved the homotopy invariance of the intersection product. I didn't use this, right? I switched to, I said, well, this thing is actually Poincare dual to the coproduct, and the coproduct is homotopy invariant, so I'm done. But I can't lift that proof to the loop space because I don't have a Poincare duality in the loop space. So I need to do something else. Okay, and so then you go and do something else. So what Paolo and Kate did is Salvatore is to what they do is in some sense to lift another proof. Of homotopy invariance of the intersection product, which is a proof that only uses this definition with capping with the Tom class. So what do we need to, what's the ID, and what do we need to make this work? Yeah, so what's the main ingredient? So the main thing we need to do, we need to compare if we have our map F from M1 to M2, which is our homotopy equivalence. We have the main thing in this definition, in the capping definition of the intersection product, is capping, right? So it's capping with this Tom class. Which somehow, let me shorten it, right? It sort of maps, it lands in this, you want to, U epsilon. We can do U epsilon 1, let me call it U M1, this neighborhood of M1, and then you have one with the, with M2, right? We have to compare these two maps. And we know it's a homotopy equivalent. So, well, F maps M1 to M2, so it maps M1 cross M1 to M2 cross M2. And you can choose, you can choose it so that U epsilon U M1 here goes to U M2 by choosing up to homotopy. We can change F to by a homotopy, or we can choose we just need a homotopy equivalent. Anyway, you can choose F Lipschitz. Well, we want, okay, let's say a homotopy equivalent map Lipschitz. So I can't spell Lipschitz. It's something like this. Anyway, you can choose it so that things that are not far away from each other, that is one of these neighborhoods, goes to things that are not far away from each other. Okay, by also playing with the epsilons, but not the complement of these neighborhoods. This is never going to be possible because things that are far away from the diagonal, well, they may hit the diagonal simply. And so there's no way you can, no obvious way you can push it out. This is, but you know, but these classes, they live in Hn mi cross mi relative to these complements, right? And it's totally crucial that it's relative to the complement. So that's sort of, yeah. That's what it looks like. Okay, so you don't get desperate. I mean, people found out long ago how to pass this problem. There is a way, there is a trick, and a good old trick to fix this, which is, well, if your map is, you know nothing about it, and you'd like it to be nice, then you can replace it by a nice map by crossing with some large space. So you pick, because you have a nice closed manifold, you pick an embedding of M1 inside some, let's say, a large ball, a disk of dimension k for some large k, and replace F by F, the pair Fe from M1 to, which is now an embedding, to M2 cross the disk. Okay, and why is this useful? Because then you can play a little bit with your tubular neighborhoods, and if you look at the diagram that says M1 diagonal to M1 cross M1, and then M1 cross this map, Fe inside M1 cross M2 cross dk. If you look at this, this is a sequence of embeddings. Every map is an embedding. This one has normal bundle T M1. This one has some normal bundle N, and this one has a normal bundle which is isomorphic to Tm2 plus, or pulled back to M1 plus a trivial bundle, because, you know, on the first factor is just the identity map. So what you get is, we have if you put this together, you get a comparison of, you get an isomorphism between the sum of these bundles, Tm1, like, you know, normal bundle plus normal bundle here, plus N is isomorphic to F star Tm2 plus Rk. And what we have gained is, we have now one equation with both our Tm1 and Tm2. So we don't, if our map is just some random homotopy equivalence, we have no a priori way of comparing Tm1 and Tm2. But now we have done it. We have compared them up to a suspension. So this is where I hope Wolfgang will tell me that I don't need to put a suspension. Okay, but, you know, so they are, you know, so we compared Tm1 and Tm2 up to, well, twisted suspension. Well, here's a non-twisted suspension, just a real, but here we have some sort of bundle. Okay, k-dimensional bundles on both sides, and so you get also, you know, an equation comparing these Tom classes and, well, up to this suspension. Okay, so we're done, right? We're done because we're done. With the intersection product. This is going to lead to a proof of homotopy invariance of the intersection product, because the suspensions are isomorphisms. In homology. Okay, this is equal to the term isomorphism. So I'm giving you, I'm not writing down all the diagrams. I could from here, write a sequence of diagrams, and you're going to have, you're capping with the one class, and you're capping with the other class, and you're capping with the sum of the two, and, we're going to say, oh, but capping with both of them is the same. But at some point, it will be important that these suspensions are actually invertible, because they will come the wrong way in the diagrams. Okay, and that's really, really sad, right? So if you follow this in the in the case of the intersection product, you can run all these things. You just need that F is a degree 1 map, or plus minus 1 map, or whatever. The degree 1 map. So F of the fundamental class of M1 is the F of the fundamental class of M2. And if you had some other degree map, you will have some coefficients in the formula. Everything behaves really well. Everything is happy, okay? But we are really unhappy, right? Because, what did I say? Well, I said, well, these normal bundles and these tubular neighborhoods and so on, when you lift to the loop space, for the Chas-Sullivan product is okay. For the Goresky-Hingston coproduct, it's becoming more tricky, right? But these normal bundles, well, they're a little bit less bad than the ones coming, the ones we need to invert. So they're coming from, or the only one that is tricky is the one you can lift these numbers, bundles. You can lift everybody, but it's not totally trivial to fix the. There are these fixes, as I said. There are 3 fixes, and 2 of them are sort of writable, and the third is probably writable too. But to know that these maps are invertible, I don't know any other way of actually using some term isomorphism at some point, which means that throwing away the normal the tubular neighborhoods was good, but it wasn't. I don't know. I find this. I was surprised by this. Anyway, yeah, that's what I wanted to say.
Question?
When you, in your main statement, you say these string topology operations are homotopy invariant. But what do you precisely mean? Do you, because the strong statement would say that well, you have an automorphism space of these automorphisms, and you want to. Let's say the weak statement would say that if you have the homotopy invariance, then the 2 string topology structures are isomorphic.
Yeah, and by the map, I have a map. If I have a map giving a homotopy equivalence, it gives me. It's an isomorphism in homology, and that isomorphism in homology respects this product and this coproduct.
Okay. And there are no.
Are there automorphisms?
Well, I understand this question. Let's say you have a fibration of Poincare radiality spaces. Can you define the string product fiber-wise? Isn't that what you're asking?
Yes. Can you do it in families? That is it.
Can you do exactly? Can you do it in families? Can you do it fiber-wise?
Probably. Yeah.
At the beginning, you said that these operations generate all the string topology operations.
I said maybe.
So all the operations you wrote down are homotopy invariant now.
Yeah.
Right. So do you see like some reason why all string topology operations should be homotopy invariant?
No, I mean, I must say that sort of I used to think it was obviously all homotopy invariant, and I think it's less obvious because it's delicate. And you know, what happens? What's a general string topology operation? Well, you have a bunch of, you want something that goes from some copies of the loop space to some copies of the loop space now in homology, and you know, with some degree, right? Some degree shift. And what sort of things do you want to do? Well, you have your p loops you start with, and you know nothing about them. They have a base point somewhere that is fixed, and then you want to look at some sort of space of self-intersecting subspace of inside here of self-intersecting things, where I'm going to say, well, this point has to be the same as this one, and maybe also as this one, and maybe, you know, this guy and that guy should be the same, and you know, these two should be the same, and whatever. I'm going to give you a collection of points, and this will be parameterized by a bunch of simplices, K1, Kp, which are going to say which, you know, the points, because these are varying points as we had for the coproduct. And once I go down to this subspace of self-intersecting loop, which is one of these coproduct type of operation, then I have a new, you know, a map from this into M, right? And from here I can read Q new loops. And how do I do that? I have to tell you what to do. I'm going to say, well, maybe you read this one. This is one loop, and maybe you go here and you do this, and maybe you go here and you do that. Something, whatever. I read a bunch of loops. I read Q of them in here. And what have I used? Well, you know, I have my circles. I have, you know, put some lines like this. This is a coproduct. I've put some lines like this. This is a product, a Chas-Sullivan product. I have, well, maybe, you know, my base point is not where it was. This is a circle action, and then I do these power operations. But it's not quite true that I can I can do this. But, you know, but the problem you get into if you go into these more general operations is now, I mean, these become more subtle to define, and you have, you know, these varying points everywhere, and they have sort of, you know, the coproduct case is quite under control with only 0 and 1 you have to worry about, and it becomes, yeah, I don't know.
Any more questions? Let me thank the speaker.